So then, welcome. I think we are in lecture 5 in parallel and distributed computing. I'm not feeling very well, but I hope you are far enough from me. I turned on the decontaminator and will not have an exercise today. Yeah, but it's good that both of you are here because we are now. This is on the recording. Because we are discussing your homework. Yeah, so this is something that I can potentially do, even though I'm a little sick. So not very difficult for me today, hopefully. Okay, so this course includes a homework that you have to do, and the way this usually works is that you form groups of 2 students. Now you have to make a decision, obviously, how to do this, and you may then call this group number whatever, whatever you think that your group is. And you make a folder in this PVR 2025 folder. There I have put into my folder, let me see where we are. See, in my folder, so Gaia, there is this Laplace 2D. I apparently have already done some stupid things here, but never mind. So in this, apparently I currently have problems with connecting to this. I don't know what happened here, but then
it actually for me as well, I have been trying past 2 weeks to connect into this SSH. It says permission denied.
Okay, no, I didn't have permission denied because I can see the tree. So your permission denied. I believe you need to be in the network.
Yeah, I have connected through VPN, Cisco.
Okay. I personally didn't had problems. Otherwise, I would. Okay, I don't know. So this we have to figure out somewhere else. So if this continues, then you have to write an email. Yeah. Yeah, because
connecting from here as well in this lab, still I face the server denial issue.
Okay, I mean because we are using only one account, right? So we all have the same account and the same passwords. So I'm able to log in, you are not able to log in. So if this persists, I'm usually not the right person. I would have to ask somebody, what would be the problem here. Okay, so if this persists, write an email. Do you have the same problem?
I haven't tried to connect.
So you haven't tried. So, okay, one of you has to at least. I mean, you're kind of supposed to work on this together. Yeah. Okay, so this folder that you saw in my subfolder, you will don't work in my folder. Make a copy of that folder to your folder, and then implement this Laplace problem that we are discussing today using MPI. So there's different which, as we noticed, we don't see it for whatever reason, but we can maybe I do a reload or something. I don't know what connection problem I'm currently have, but previously I was able to log in and make this copy. Yeah. So what I wanted to point out is that there are several files that all solve the same, that are all supposed to solve the same problem. And this MPI, okay, yes, I don't know why this is actually opening. So I guess this is still in the cache. This is why it's opening. So MPI is, of course, there are, of course, different ways how you can implement this in MPI. You can implement it in blocking, in non-blocking. You can do it very clever, less clever, and so on. Yeah, I mean, the minimal solution, so actually, I would like you to do both, yeah, and to be as clever as possible, trying out as many things as possible. But really, the minimal solution to get the tick on you did the homework is doing one of them. Yeah. I mean, this is you don't get a mark for this. But later we have an exam, you know, where you have to write programs on paper, and for this, for the exam, this is an exercise that you should do. This is why, I mean, it's you're ticking the mark if you're doing one of them, but I suggest that you do both of them just for the exercise for the exam. Yeah. If not, because you want, of course, you come here to learn something. So so the one, because now I'm not able to open these, I cannot tell. Okay, so the main serial version is one that is already implemented here, and where you can use this as a template, seeing what happens. And then there is different versions for different ways of doing parallelization. Yeah, so we can parallelize with these threads. We can parallelize with CUDA. CUDA runs on the GPU, and we can parallelize with OpenMP. So OpenMP is for shared memory. Parallelization, MPI is for distributed memory parallelization. So threads, OpenMP, and CUDA are things that we will discuss in forthcoming lectures. Yeah, so MPI, we've already covered some ground on MPI. Yeah, and this is the way you should do your parallelization. Okay, so then yeah, you're supposed to do this, and then you should upload the results till the 13th of July, which is a Sunday. Always, I mean, you're supposed to do it on Friday, but I leave you the time till, I'm not looking into it on Sunday. It just, there's no reason for me to not, you know, give you the weekend if you like to work on the weekend. Yeah. And then, yes, we do an appointment, and then you have to present this, and then hopefully we are happy and you pass this, and then we go on for the exam, right? Yes.
How long is the presentation?
Okay, so nothing. Yes, let's make it 20 minutes. We are not very stringent. Maybe we should be stringent on this. Yeah, we are going to ask some questions later. So it will be you show something, and either I ask in between, and then it, I mean, okay, because I may ask something in between, then it may get longer. So but you could plan for 20 minutes if there's no interruption. Yeah. Okay. Sorry for me being.
Presentation is combined.
Combined? What do you mean combined? The two?
We both should be doing a
You're doing one. Okay, you two
individual.
give one result.
Okay.
Yeah. So this is why there is no mark, because I cannot judge who of you did what. Yeah. So these things where we don't. We encourage teamwork and so on, but we at the end we have to give marks for individual work. So here you have a homework together, you do your presentation together. Yeah, you can also decide one person is speaking, the other one. Yeah, that's up to you. But it's therefore there is no mark to it. Yeah. And I may, okay, so the other thing is, of course, I can ask any of you anything. Yeah? If I have the impression that everything was done by one person, then I may ask the other person to explain it. Yeah? Okay, so what is the task? The task is relatively simple simulation project where we want to solve the heat equation in a static format, and say we have something like this. You could think about this like a metal plate, yeah, that has 4 sides and 4 different temperatures. So don't bother with this number. Say this would be decreased. It doesn't really matter. Yeah, it's just 4 different values on 4 different sides. Okay. So how are we going to solve this? So usually there is this Laplace equation that describes diffusion, where we have the change of u. Okay, so this is the way in this problem they describe the temperature. U is just the value that we solve the diffusion equation for. So there's a time, so this change in time, and this is then equal to a diffusion coefficient and the sum of the second derivatives. Yeah, so this is the Laplace equation. Why is there a t? So yes. Now we are interested in the static solution of this. So basically the case when dtu does no longer change. So when this becomes, or if this is 0, when the temperature does no longer change, when this is 0, so you see this equation becomes independent of k in that case, right? Because then you can divide by k, as k is not 0. And so what we are going to do is in pseudo time, yeah, we just do a kind of an Euler forward integration. So where we have our time step t, so our time t ut plus delta t is, if you remember your numerics class, yeah, Euler forward integration, you are familiar. You are, so one is nothing. No, not really. So, okay, so you do an approximation Okay, so how is Euler forward working? So this is the time derivative, right? So you can, the equation gives you an expression of the time derivative. And now if you think about first order Taylor expansion, yeah, of a value at a different position, so t plus delta t, so it's a value itself plus the distance that you walk, that's delta t, yeah, times the derivative, so it's delta t times dtu. Yeah, so dtu, you know from the equation, is this thing here, right? So this is what we call Euler forward integration. So now we replaced the time derivative with the spatial derivative. In the spatial derivative, we compute from central finite differences. But you're familiar with central finite differences? No? But you are familiar with central finite differences, yes. Why, so what was your subject before?
Mechanical engineering,
They don't have numerics in this?
no, no. I don't remember. I think that's the Euler quota or something like that. Not the other one.
Euler what?
Euler quota,
Quota?
yeah, some approximation for that.
So this
Yeah,
This is the Euler forward integration. So Euler is in the word, yes, in the name.
Yeah, but I thought it was
Euler integration. So these are finite difference. These things here are finite differences, second order finite differences. Yeah? So they can be derived from a Taylor expansion. Okay, so when you work together and you know you are on different levels, then please explain. Okay? So this is a way to approximate the second derivatives. Now, now we are combining these two things together. If we combine these two things together, we'll actually have the following here. We'll have minus 2 times the one in the center, and you see this thing here is the one in the center. Yeah. That if you combine these in a clever way, and the clever way basically is deciding that delta t is, so the length of one time step is delta is h squared divided by 4k. So we make the time step dependent on the diffusion coefficient. Then we have combined it in such a way that this guy here together with these two guys there cancel out because there's a minus in here. Yeah, and all that is left is the 4 neighbors. And what we can then compute is that in the next time step, u is this combination of the u at these 4 neighbors that it had. Yeah? So this is basically the diffusion. You take your 4 neighbors, yeah, add them together, divide by 4, and this is the next time step. Okay, now, I mean, the idea here is to do the most simple numerical thing possible. You can do more complicated numerical things, but we choose this simple example here so that we can actually focus on the computation part and don't think too much about the numerics part, yeah, because it's so simple. Okay, now this thing obviously has some boundary conditions in this up, down, left, right states. And these are introduced through additional cells that we put out around the domain. Yeah? So that's what we have here inside, this blue thing here inside. This is the domain where we solve the equation. And all around this, we put a given solution to that equation. So, for the numerics people, is this a Dirichlet or Neumann boundary condition? So you already indicated that you don't know. So, Dirichlet or Neumann? Now, what is the difference between Dirichlet and Neumann boundary condition? I mean, don't you know now or don't you know ever?
No, I know.
Okay, so yes. Yeah. I mean, because this makes a difference for how I explain. So Dirichlet, so Neumann boundary condition is a flux boundary condition. Yeah? And Dirichlet boundary condition is a value boundary condition. So obviously we set the temperature, which is the value we are solving for. Then it's a value boundary condition, and then it's Dirichlet boundary condition. Yeah? So Dirichlet boundary conditions we can implement in that fashion, that we simply set additional nodes or cells outside the domain and set them to a fixed value. Yeah? So, and these are usually easier to implement than the Neumann boundary condition, and this is also a reason why now we want to keep the numerical part simple. We here only use Dirichlet boundary conditions. So, then we have, aside of talking about your problem, we have to do a little bit of theory even today with regards on how you are going to access your data. And we'll see this can actually make a considerable difference. Now, this problem is a problem in 2 dimensions. Usually, if we solve physical problems, we are in 3 dimensions, but sometimes we also have 2-dimensional problems, right? So now we have to cover this 2-dimensional or later maybe 3-dimensional problem inside our computer, and computers always use 1-dimensional memory layout. Yeah? So basically what this means is if you have a multi-dimensional problem, what happens in your memory is that your problem is always cut into pieces, or the piece, or let's say the different dimensions are flattened into just 1 dimension. Yeah? And this can be done in different ways, and depending on your computer and your programming language and all, and how you do this is actually done in different ways. And there are very simple ways to do it and very clever ways to do it, and they vary depending on what you want to do. So very simple way of doing it is just to, take either the rows or the columns and, stick them together, one after the other. And then you have to process your data, and because you're in multi-dimensions, you have to iterate over these dimensions. For example, you iterate over x and you iterate over y. Now comes this question, that you have to ask yourself, is it better to iterate over x first and then over y, or over y first and then over x? And you wouldn't imagine what difference this makes. Actually, that's a fun thing. I was recently at the IIT Madras to give a course on lattice Boltzmann, where I implemented small codes, and then the students, they had to modify it, and the student came and said, so I made your code twice as fast. Yeah, and how did he do it? So he just told me I was not properly doing the order here. So he just changed one line, from x first then y to y first then x, and the code was twice as fast. Yeah, so that's not. I mean, of course, it depends a little bit on the size of the system, but this is not a small thing. So, how are these things actually, counterpart? So, if we have a static C array, what this actually does is, or a multidimensional C array, then all this does is it's putting the rows next to each other. Yeah. So this here would be the initialization of a static matrix. Yeah, static means that at compile time you already have to indicate the size of the thing. Yeah, so this is how it works in C. So it has three rows of 4 columns each. Yeah. So, but they're simply stitched together, so you can do the same thing here. Yeah, that's exactly the same. So this way of stitching data together, where we have the first row first, and then the second row, and then the third row, that's called row major, and this is the way in C or in C++ arrays are stored, which is something important to remember. Also because that's not necessarily the standard. Yeah? So there are different programming languages that do it in different ways. So row major means that the fastest changing index is within the row. Within the row. So you are going. So data is stored along this line. So there is A11 first, then comes A12 and A13, and so on. And so this is stored in that way, and this is how all the C-derived languages deal with data. So C-derived languages like C, C++, C#, Objective-C, and say also Java is a C-derived language, right? So they are all row major. Now this is not all languages work like this. So basically, what computer scientists distinguish is they have C convention and Fortran convention. Yeah? So lots of things are done in C this way and Fortran that way, because C and Fortran are the big programming languages that have been around and that have inspired other programming languages over the decades. Yeah? So here, you know, there's this row major is basically a C convention, and then there is Fortran convention, and then from Fortran other languages have been derived. You know, you have MATLAB, you have Julia, SR, Skylab, and yeah, what not, I don't know, but these use Fortran convention, and they use column major, which means they store their matrix in the opposite way. So the fast data, so they have the first column, and then they stitch on the second column, and then they stitch on the third column. And it's important for you, when you write a code, that you know whether your programming language is a row major or a column major, because then you do it in the opposite way. Yeah? Here we use C++. So we need to know this. But okay, so there is one more complication to this, namely dynamic arrays again work in a little bit a different fashion than static arrays, because in a dynamic array what happens if that inside this inside the row of the array, if you will, you have the pointers to the columns. And this makes it column major, such that you have to deal with this in a column major fashion. So in C++, you could have, for dynamic arrays, you could have column major, and for static arrays, you have row major. Okay? So you need to take care. So if you have this pattern here, this basically column major pattern here, is that you do the column most inside of your loops. So you will have y as the most inside direction, and you iterate over y first, because this is the fastest direction. Yeah. So you'll only when you go through the entire y direction, you increase x, and this is why this is the fastest. The inside is supposed to be the faster one. By the way, why would we care about this anyway? I mean, we have random access memory. Why do we care whether we access data consecutively or in random order? Yes, why is it faster? I mean, I come from a time, I'm so old, and I come from a time where this didn't matter. I mean, this thing is called random access memory because it was always, as you know, from the modern perspective, it was always equally slow if you do an addressing. Now we have invented Now what happens? We have broad buses, we have cache lines, yeah? So what the processor does is it is actually not addressing single places in memory, but it always reads and writes lines, cache lines of memory. So it always takes, consecutive data together that reads together and writes together. And so it is fastest if the data that you process is already in the order of the cache line. Yeah? So if your fast index is not aligned with the cache line, then you always access one value of that cache line, then you discard this cache line, then you take another one. Yeah? So in particular, we talked about memory bound operations. If you are memory bound, yeah, and you use only one value of each cache line, your execution could be like factor 10 slower. Yeah, I don't know how large cache lines are actually now. But you would be significantly slower if you comp against the cache line as if you are along the cache lines. What is this doing? Okay, so this is the reason why we care about fast index and slow index, right? So, and the fast index always has to be in the innermost loop. Yeah, and this here would now be column major in a dynamic array, so we will have y in that case innermost. Yeah, and if we put x innermost, then we would be slow, while when we have a static array, we would do it the other way around. Yeah? Okay. Now the thing that I unfortunately could not show you, because I don't know, because I'm not properly logged in, is the code that we are going to use here for our example, which we've already implemented in the serial version. So the serial version is already implemented. You can take this to start your own program. And in this, we use a 1D array. So this is very common in numerics that we do our data handling ourselves, yeah, and we use a mapper function. And this mapper function just maps the two coordinates x, y to this 1D array. So in that way, we can allocate this dynamically, but we don't put lots of pointers to the different columns, which is also important because so we don't need to go through a pointer each time. Yeah? So in that case, we are back to column major. We are back to a column major implementation. So we have to put the column. Row major. Yeah, we can easily confuse us with these things. We are back to a row major configuration. So we have to put the row, which is the x variable, innermost in the loop. So then this here would be faster than that one. And if you're interested, how much difference this make in your program, you can try it out. One thing that I have to tell you is that if you run this problem pretty small, and it's usually a pretty small problem, then, and it fits completely into the cache, so it may not even leave the cache, then you may not even see the problem. But once you run a problem that is larger than the cache, then it makes a big difference. Okay. Basically, this mapper, which we have a class here, is implemented like this. So you see, the fast variable is the x, and so if you change x by 1, you just increase. You go to the direct neighbor, while when you increase y by 1, you jump over nx. So nx is the width in x direction. You jump over nx neighbors. Yeah. So this is why you should have x as your fast variable in your iteration. Okay, so these are other functions like so the inverse function, so you can get x from the position or y from the position. Right. So, because I'm not properly logged in, I can't show you this, but you can download later the files. So what you're supposed to do, unfortunately I've already apparently done this, you in your folder, you can delete what I've already done and make a new directory build, yeah? Then you change into the build, and then you use something that is called CMake. CMake is a program that makes makefiles. You know what a makefile is?
Under the folder, create a new file.
So make.
Under a folder, to create a new file.
Okay, yeah. So no, okay. The make. You know, my question was, what is a makefile? No, I'm not. No, makefile is not me asking you to make a new file. No, makefile is okay. So makefile is kind of a script that tells the compiler what to do, because there are so I need to know, if you don't know what a makefile is, then please say I don't know what a makefile is, because there's no point. I assume that you know what this is, and then I go on and you don't know, yeah, because here.
I don't know exactly what it is.
Yeah, but if you have an idea what it, there's this.
We are wrong. I don't know. I don't want to say something wrong.
So you don't want to say something wrong. Yeah, okay, sorry. Yes, maybe I don't, me myself, I have to admit, I don't 100% know what is going in this make procedure. But the thing that makefile is a kind of a script that you call by make, yeah, that calls the compiler, the linker, and builds together all the files that you need for your project, and makes maybe it's generating subfolders and so on. Yeah, can be complicated or simple. Yeah, and later produces your executable. Yeah, that's what the make file does. So, and then, I mean, after you made it, so this CMake, the CMake file that is already included makes the make file, and then it will make the different versions that have been implemented there. For example, Laplace serial, and then this you can run. And the way you are later supposed to run this is not on the login nodes, but to use it on the batch system. And for this, we use sbatch job file. I think Konstantin already mentioned the job files at least, and we had maybe we'll repeat this next week again. Maybe that's useful. Yeah. So the thing with the job files is so if you log in and run the code, it will run on the login nodes. The login nodes are only in the cluster to actually get a handle to the outside that's communicating to the outside world. This is not supposed to do any computation. Computation is supposed to happen in the batch system where we have the compute nodes. So all the workers. And the way this works is there's a job file that describes your job, saying, for example, what you need. So you need MPI, you need so and so many cores, you want to run this, and on that, what is it? So you can choose different queues, yeah. So different queues for different, your different requirements. So there could be queues that allow you only to run for 20 minutes. There are queues that run long time. There are queues for the so-called fat nodes where you have a lot of memory. There are queues for the GPUs, queues for the CPUs, yeah, so different queues. So this job file includes these parameters and then sends it off, and then it's in the queue, and once it's there, there is time for Phoenix to do it. Phoenix will execute this, and then you get to see your results. Okay, now how's this supposed to be done? So the very minimalistic solution for your homework would be to divide everything in at least 4 parts. But I suggest that you make it more flexible and allow it to be an arbitrary number of parts. Yeah. So what we are going to do here is what we call domain decomposition. So we have a domain of a certain size, and we attach different parts of this domain to different compute nodes. So we decompose the domain, in that particular example, into 4 parts. Yeah? 0, 1, 2, and 3. So because we are doing this in MPI, and we have distributed memory, what we are going to do is in each compute node, we allocate only the part of the domain that we actually compute. Yeah? And we have to make the decision what we compute according to our own name. Our own name in MPI is called our rank. So we have to identify our rank. Yeah? And then from there on, we know which part of the domain we have to compute, and then we do this computation there. And then the important part is, of course, the communication. So things have to move from one part to the other part, from one process to the other process. And now you have to remember, again, that we are using a distributed memory system. So no way to access. So what is the problem? The problem is that here you have these cells that you want to compute, and these cells don't have any neighbors to one side. Yeah? So you cannot, and you're using finite difference, so you need information from the neighbor. But you cannot access the memory of your of the neighboring process because you're in a distributed memory system. So what you're going to do is to extend your domain with one layer of nodes, which you use as a boundary condition for this inner part, and this boundary condition is set by copying data from your neighboring process. Yeah, and fill this in here. And this is done so for all the interface positions. So what you have to do is you have to introduce a so-called ghost layer. Yeah? So you have to extend your data here so that you have place to copy something into it. And then this is, of course, done through send and receive buffers. So, for example, the send buffer, you have to get data out of your domain, place this into a send buffer, and then you'll do the sending, where on the other side you have a receive buffer. Yeah? So you send this off, you get this in the receive buffer, and after receiving this, you put it into your ghost layers, and then you go on with the computation. Anything surprising with this? No. Okay, our MPI steps that you have to do. Well, okay, so you have to partition your setup, and then you have to do the initialization, which means you have to initialize the MPI process, and you also have to initialize your data. This is something that in C you always have to do, so you have to put, for example, zeros everywhere, yeah? And then you loop. Okay, no, yes. Okay, so you initialize first. So you say you put everything to 0 first. Then you loop. Okay. And then you hopefully remember this philosopher problem that we discussed last week. So what was this philosopher problem? Did I call it philosopher problem? I think I said ring exchange, right? Ring exchange.
No, you started and you said it is, and then you
hoping that I explained it clearly. Okay, there was a ring exchange.
I get it.
There's rung 1,
Two.
rung 2. Okay, don't make it too. Okay, let's. So now they all want to communicate in a ring. Yes,
Yes.
you remember that.
Yeah.
So, do you notice that this problem here has the same challenge?
Yeah, with the send buffer, receive buffer, and the ghost layer, it has to come again to.
Yeah,
Again
so
to the ghost layer. We have to assign it back to ghost layer.
okay, so this is not. mm, Well, the problem is that all of them want to send something to a neighbor in a certain direction. So if they all start off doing this the same way, yeah, then they get locked. Therefore, you have to break this circle, and the best thing you do is you so okay, basically you do the okay, now this is a stupid picture. Okay, maybe I have the picture. I think I have the picture here. Yes. So what you do is you distinguish between even domains and odd domains, and the even domains start with sending stuff to the right or exchanging to the right, and the odds exchange to their left. Yeah? Let me see whether I have this picture here. So, you know, this guy, for example, is first sending, while this here is first receiving. And then afterward, you do it the opposite. Okay, so you have to do two things. So first, along a row, yeah, actually you would break along the row. It is actually like this, that you wouldn't get stuck because you have there is one place where you don't have a neighbor, right? Because it's finite in one direction. Yeah? But this would, so in principle, if they all try to communicate in the same direction first, saying to the left, yeah? So they wouldn't get stuck, but what would happen is that the last one would have to, in the last one in the row, would have to wait for all of them, for all the others to actually reach there. You know what I mean? So you are in one line, and all of them communicate here. So then, so this guy here is not waiting for anybody on its left, right? So this can communicate directly here. So once this has arrived, then this can communicate here. Then when this has arrived, then this can communicate here. Yeah, in a blocking communication. So, which means that this here, so this communication between the last two in the row cannot start until everything before has been done. So this is why we don't do it like this, but we changing the direction every other step, so that they can go, so that every second of them goes one way first and then the other way back. Was this my explanation that was not clear last time? Apparently last time it was not clear what I explained.
No, this was.
Okay, so that was clear, good. Yeah, so, you know, this is what it says here. So even exchange with right, odd exchange with left. Of course, you can also do even with left and odd with right, yeah, but just one way or the other, yeah. And then you do bottom and top, obviously, in the same way. Also with even and odd. So then you have to be sure that everything do the calculation with the ghost layers. Yeah, okay. Now, while you are sending stuff around, now if we want to be very clever, yeah, this sending stuff around, this may take some time. Now you can do a synchronous send and receive where you have to wait, or you can do this asynchronously where you allow the network, you know, to send stuff around. Yeah, you send off and then you do work and then you call wait and see whether it has arrived. So, I mean, what I want to say is during the time you do communication, you can do other work. Yeah? As long as the work does not depend on the data that you have been sending around. So in this example that we have here, the work that we can do in between is very limited, but this is only because it could not be drawn otherwise here. So the work that we can do is doing the computation in the part of the domain that is not connected to the boundary, which in this picture is just one node, but suppose we have a bigger subdomain that may be many nodes, right? So you send stuff away, and while you are waiting for this to arrive, you are doing the calculation inside your domain in the part that does not depend on the interface. So, once you're done sending, what you do is you calculate all these things. So first thing, of course, you load the buffers into your matrix. This you have to do first. And then you do the calculation inside the domain. So what is kind of a little bit unrealistic, and this is because this example, as it is shown here, is so small. Yeah. So you see, here's more surface than there is volume, if you will. Yeah, because we had only one node that was inside the domain, and now we have 8 nodes that are on the boundary of the domain. Yeah? So usually you have more nodes in the inside of the domain, but in this example it's the other way around. So after communication is finished, you do all the other computations. So this is what we call communication hiding, because this communication usually takes up a lot of time, communication over the network. But if you do proper communication hiding, like you do enough work during the communication while you are waiting for your data to receive, to arrive, you can actually get this communication for free. Yeah? Because you're doing something else in that time. So once you call wait and the work is already done, wait will immediately return, so you don't need to wait. And you can just go on with your calculation, and so the communication has been for free with respect to time, at least. Yeah? So, and if this is the case, then you have perfect scaling. So you do bigger domain, yeah, with more, for example, you have weak scaling, bigger domain, more processors. You get so you get from you double the nodes, you double the processors, you will have double the updates. Okay. So clear what I meant with communication hiding. Yes, and then, okay, so you do the calculation okay, so the last thing we need to do after we do the thing with the buffers again is to do an output. And there are different ways of doing this. So if you have really a big problem that you want to solve, you can have a distributed file system, yeah, where every process writes their own file and you connect these files later together. This is what we usually do. But since this is relatively complicated and our problem is relatively simple, what we do is we collect all the data to one of these processes and let one of these processes doing all the output. So now we collect this at rank 0 and then we write out the file from rank 0. So this would be sending everything into the same place. And then we are done, and the one thing that I'm a little bit confused now is we are missing. Okay, I don't know why this is missing here. Let me see. We are going to use a software that's called ParaView. So this is one thing that you have to download and install. Yeah? So we can use Phoenix only from the command line. This means we cannot display our results with ParaView, but we can write out the file. And there's a file writer already implemented, and you will see this in the serial version of the code, which we now cannot have a look because I'm not connected to this. But once we have this, you can download your file that has been outputted, which again I cannot do now unless I have the version from last year. Let me see. What is this? We are in distributed computing. I don't know whether we have. I think I did not download it here. Did I download it here? Example Laplace. Ah, yeah, right. So there will be a file that's called temp output IMP. So I can now go to my documents, and so this is where I simply have it. Distributed computing. So this is now, of course, okay. So there is. I'm just let me see whether I can load it. So okay. Now we loaded this file. We also have to, ParaView. You always have to tell it that you actually want to do something. So ParaView, which is a good thing, because ParaView is a software to handle enormous output files. Yeah, ParaView means actually parallel visualization, whatever environment or so. Yeah, so that can also read distributed files. We are just using very, very small portion of this. So one of the big problems that you may have with standard software, if you open a file, the software will try to read that file. Yeah? Which you can imagine, if your file is 30 gigabytes large, this will get your computer stuck. So with ParaView, it's a good thing that you only tell it, okay, give me a handle to the software, and let's see what I want to do with it. Yeah. Okay, let's apply this. So it's actually reading it, and we already get the temperature. Now it's here very simple because there's only one data array in it, which is the temperature, which we already get to see here. So, the software can do a lot of things. All you need to do is to open the file, press apply, and then you see this result, and hopefully your result will then look the same way. Yes, and I don't know whether I should show you anything that we can do here. If you like other colors better, you can, for example, use this here. Again, press apply. Then you see it in a different format. Okay. So, unfortunately, we cannot look into the code. If you have any more problems looking in the code, then please write me an email. Then with the login, yeah. Then write an email that we can look into this. I think I would potentially just need to restart it. I think this is all the problem that I have. How do I don't. I have a strange problem here. Well, let me try one more. it didn't open. Okay, so this is our Phoenix. So, okay, I just have to enter the password. I mean, I don't get a permission denied, but okay, yes. So this is not what I wanted to see. I wanted to go to serial. So sometimes it asks you for the password again. I don't know why. Okay, so this is, you see, this is the serial version of the code. What on earth is this? It doesn't make a lot of sense to ask now again and again, because it already opened it.
No, this is the same issue I'm getting. Asking for the password again and again.
Okay, I don't know what this, but anyway we have access to it. Yes. Okay. Let's just briefly. So there are a few standard stuff that we are loading here, and then there are a few files that we also load. For example, mapper 2D. This is the one that unrolls the matrix. Then there's parameters for the simulation, and there are some utilities that is, I guess, is the one for writing out the file later. Yeah. So what you do here is you have one-dimensional vectors for old data, new data. You initialize them with 0. And also what you do here is along the boundaries, you set the boundary values that are written in the parameter in this file parameter .h. That's where it's getting from. Yeah, you start some timer and then you do some iteration. It's already prepared for, even though it's a serial program, it's already prepared for the MPI version, where we do the inner calculations first. So this is actually the equation, and I guess we have, okay, this has only inner iterations. So after we did one time step, we swap the old data with the new data, which is just an exchange of the pointers. And then we do this output file. Let me see. Okay, as you see, it's saying this again and again. So CD PV R 2025 Explorer Okay, let's go here. We are in this. Okay, so there is a make file, I guess, build tests, src make file tests. So you see now I'm badly prepared because it didn't work before me. So as I'm looking actually for the job file, where's my job file? Build bin OpenMP. Okay. Okay, okay, maybe I did not actually build it. That's possible. So okay, you know, because I'm not. I should actually go back to my bed. I let you play around a little bit with this, and I hope you find this thing in here, and you, as a homework, you try to compile this the way it is indicated in the lecture notes. I'll upload the lecture notes in a few minutes. And then next week, if there has been any problems, we'll talk through this again and see where we have this job file and how to run this. I think this is now okay. A little bit cut short today, but. Yes, I'm not particularly well today. I hope this is not going to cause you any problems. Let me stop the recording. Not even that works.